Okay. Okay, folks. I think we're on. Let me grab the lights here. Okay. So, folks, so far in quadratic relations, we've only worked with any sort of quadratic in like this form, right? That ax squared plus bx plus c. And that's what you call standard form. We call that standard form in quadratic. Lovely. Usually, I would say a good chunk of the time, quadratics will be in that form. So for example, a lot of them will look like this: x squared plus 5x plus 6. Or sometimes even like negative 2x squared plus 3x minus 11, or something like that. Those are quadratics in standard form, and a lot of the times they are like that. Now, when these quadratics are expressed in the standard form, we can easily identify the y-intercept. And the y-intercept is easily identifiable because it's just that c value, that last term. That quickly tells you the y-intercept. It's lovely. And the other thing it tells you here, it tells you whether the quadratic, or the parabola, right, tells you whether the parabola is opening up or opening down. And that's based on the a value. So if that a value is positive, it opens up. And that's this a value right here. So for example, I know there's no coefficient here, but we know it's positive 1. So we know that, the coefficient, if there was a positive 1 here, which in theory there is, we know that that quadratic is opening upward. It's happy. It's creating a smiley face, yeah, which also tells us it creates a minimum. Then you can have one like this, negative 2x squared. And because that a value is negative, it tells us that it's frowning. It's facing downward, yeah? Which also creates a maximum point, which we investigated last week. Okay, now, very similar to linear relationships, where sometimes the equation of the line can be in y equals mx plus b, and other times the equation of the line could just be a pretty big mess. And we learned that a lot in the linear systems unit. Remember how sometimes you got to do substitution or elimination. Sometimes you have to rearrange that formula to get it to what really you want to do. Similarly, quadratics are not always expressed in standard form, which we love standard form, we really do. But just as much as we love standard form, we love this form right here. And this is called factor form. It's y equals a, and then x minus s, x minus r, both in brackets there. And it looks a little strange, but we'll take a moment and write that down, and we're going to talk about r and s. It says such that r and s are just integers. So they're numbers. Not fractions, they're numbers. And we call this form factored form. This is good stuff. We're getting closer and closer to factoring. Now, the reason why we would ever want factored form is because, well, it tells us great information, arguably more information than standard form would tell us. So firstly, we also know the direction of opening from a quadratic in factored form because it's got that a value right here, right? The a value here and the a value in the standard form really are the same thing. Now, what else does factored form tell us? Well, here's the big one. This is the huge one. This is the reason why we love factored form. It's because it tells us the x-intercepts. It tells us basically the zeros or the roots or whatever you want to call them. the values of R and S. And that's these guys right here, S and R in the brackets. Those are actually the roots of the equation. What else does it tell us? Well, I guess from the x-intercepts, because quadratics or parabolas are symmetrical, if we have the two x-intercepts, we can simply solve for the vertex. We'll get the x value of the vertex, which we know as the axis of symmetry, which is really just in the middle of the x-intercepts. And we could sub in that x value to solve for the y value of the vertex, which is what we did a little bit of last week, but we'll certainly do it again today. Like I said the other day, or the last time we were here on Friday, I'm like, I'm just planting a little seed for what's about to come, and here we go. This is it. Yes, of course, the axis of symmetry. So, for example, maybe I can draw a decent sketch here. If this is our graph, yeah? It's nice. Although we don't have the y-intercept, that's okay. What we do have are these two guys right here. These are the x-intercepts, because that's the x-axis. We will get that. And from those, we know, like we investigated or explored the other day, that in the middle of these two x-intercepts, because a quadratic is symmetrical, somewhere in the middle of this thing, that is where the axis of symmetry is, right in the center. And we also know that the vertex, that point right down here, that point of changing direction, the vertex lies right on the axis of symmetry. So it shares the same x value. That's why having the x-intercepts is so good. Because once you have those two symmetrical points, you can almost do anything with a quadratic. So sometimes you'd be given an equation. Let's just look at this first one on the left here. Here's an equation. We're going to look at the zeros, the axis of symmetry, like the equation of the axis of symmetry, how to get the vertex, how to get the y-intercept, the direction of opening, the maximum or minimum, and then the maximum or minimum value, all from just one equation. Yeah? So firstly, if we want the zeros, yeah? If we look at that and say, okay, 2x minus 4, x plus 2. If we want the zeros, what we do is we set each term in the bracket equal to 0. Remember, the equation is x minus s, x minus r. So here, x minus 4, we're going to set that equal to 0. And same with the x plus 2. These are zeros for that reason, because we just set them to 0. Now, we should solve for the x-intercept. So when we solve for x, we have this minus 4 here that we're going to take and bring to the other side. So we really just get x equals positive 4, and that is one of the x-intercepts. And Gabriel looks at me like, what, why would you do that? Well, hold on. That looks like a weird, simple move. It's like, well, Mr. Yakovich, why didn't you just change the sign? X minus 4, why don't you just change it to x plus 4 and call it a day? Well, I would certainly get into the habit of taking this term and moving it over, because sometimes it won't pan out to be a nice integer as an x-intercept. Sometimes it'll be a fraction. Now, if you're wondering what it looks like on a graph, perhaps we can pull up Desmos here. Desmos. And let's graph this thing. We got y equals 2, x minus 4, x plus 2. Close the bracket. And if you look at the x-intercepts, yeah, we got 1 at positive 4 right there, and 1 at negative 2 right there. Isn't that lovely? So good. Okay. Next, the axis of symmetry. Well, if we have the graph, it's so nice. You can almost point at it. Given this graph, you're like, let me zoom in a bit. It's a left. The axis of symmetry, what's between 4 and -2? You know? This is on a nice graph. It's nice to see. What we are going to do is this. We're going to say, okay, the axis of symmetry is going to be S plus R divided by 2. We're basically just taking the average of the x-intercepts. We're going to add them together and divide it by 2. So we're going to do something like 4 plus -2 divided by 2. 4 plus -2 is 2 over 2, and x equals 1. So yeah, that axis of symmetry exists at x equals 1. So far, so good. And if we go back to that graph, I can put in that axis of symmetry right there. Isn't that nice? Right down the center, and it is down the center, we can see. Now it's like, well, what do they want next? The vertex. Well, we know that the axis of symmetry at x equals 1 goes right through the vertex. And now this is telling us the vertex is 1, -18. That's great. But how would we get that without the software? Well, just like we did the other day. We know that our vertex so far is 1, something, right? It's something that's there. So what we're going to do is we're going to substitute the axis of symmetry, which is x equals 1, into the equation. So what would that look like? Well, our equation is y equals 2 bracket, and it'll be x, which is 1, minus 4. And in the other bracket, we got x plus 2. Then we just go ahead and bedmass this thing. 1 minus 4 is -3. 1 plus 2 is +3. I go to my calculator. 2 times -3 is -6. So maybe I'll show you this. -6 times 3. And that is -18. So we now know that the vertex is 1, -18. Which the graphing software confirms for us and says, yeah, you're right. Remember, it was 1, -18? Good. Now the y-intercept, I told you that, well, we can't actually get the y-intercept just by looking at the equation. That's what standard form is for, right? However, where's the y-intercept here? It looks like it's at -16. I wonder how they got -16. Does anyone have any ideas on how we could possibly solve for the y-intercept? Well, the y-intercept exists when x equals 0, right? So we're going to set x equal to 0, just like we did in grade 9 for the linear equations. So we'll say, okay, y equals 2, and we'll say 0 minus 4, 0 plus 2. I get 2 times -4 times +2. I'm running out of space here. 2 times -4, -8 times 2, -16. So the y-intercept is at -16. Like, look at all this information we got from just the standard form. Sorry, just the factored form. Direction of opening, up or down? Yeah, it's opening up. And how do we know? A value is positive. Absolutely. And if it's opening upward, is that a maximum or minimum? It would be a minimum. Minnie Mouse is smiling. Yeah? Now, what is the maximum or minimum value? Does anyone remember from the other? Yeah, what do you think, Julie? Why do you think that? Yeah. -18 is the minimum value. Or perhaps we could say the optimal value. But yeah, that's the thing about the vertex, right? The x value of the vertex is the axis of symmetry, and then the y value of the vertex is the actual optimal value. And sometimes, for me, I mean, it feels so much better to just see it on a graph. And notice how, yeah, that minimum value you can see here is at negative 18. Okay? Questions about that? All right with that? Okay. The next one. Y equals negative 4, x minus 4 squared. Okay, let's see what that looks like. Y equals negative 4 bracket x minus 4 squared. All right. Interesting. How many zeros do we have here? Meaning, how many x-intercepts do we have? Just one. Yeah. And look at the way this thing looks. And I told you the other day, this might be a special case, right? Remember I said when there's 1, 0, it's a very special case. And this is what they look like. So we're going to take the 1x value that we have here, which is x minus 4, and we're going to make it equal to 0 to solve for the 0. And when we bring that negative 4 over, we get positive 4. There's only one 0 right there. It's at positive 4. Now it's like, well, where's the axis of, how do we get the axis of symmetry? Well, see how this is squared? Yeah, see that? Really what it's referring to is this, x minus 4, x minus 4. Because when something is squared, it's just multiplied by itself. Yeah? So in theory, there are two of the same x-intercepts. One's at, x equals 4, and I guess there would be another one at x equals 4. There's really two of them on the same point. Okay? So that being said, when we solve for our axis of symmetry, you can say s plus r over 2. We're going to say 4 plus 4 over 2, and we will get 8 over 2, which is just 4. Now, eventually, you're going to get so good at these that when you see a quadratic that looks like this, you're going to know that that's a special case. You're going to know everything about it. You're going to know that there's only one x-intercept, and the x-intercept is the same as the vertex and things like that. Okay, we wanted to solve for the vertex here. Like, yeah, we're gonna sub this in. We're gonna sub x equals 4 into the equation. So we got y equals negative 4 bracket 4x minus 4 squared. So we get negative 4 times 0 squared. 0 squared is just 0, and negative 4 times 0 is 0. So our vertex here is the 4, 0, which, again, we shouldn't be too surprised about because this is a special case. This is where there's only one x-intercept. And whenever there's only one x-intercept, the only possible outcome is that the x-intercept is, in fact, the vertex. That's the only possible way there could be one root or one x-intercept. And that's what the equation will always look like. X minus 4 squared, x plus 7 squared. And you're just going to know just by looking at it. That's how good we're going to get. Okay, next, the y-intercept. Well, just like we solve any y-intercept, we set x equal to 0. So we grab that equation again and say, okay, well, y equals negative 4 times 0 minus 4 squared. Negative 4 times 0 minus 4 is negative 4 squared. Be very careful here. Negative 4 times positive 16. Negative 4 squared is positive 16. And we should get something like negative 64. Anyone else? Yes? And let's go look at our graph on Desmos, just to confirm, just so we can go to bed at night knowing that Okay. Isn't that nice? You're like, oh, okay, good. Direction of opening, is this thing opening up or is it opening down? Well, we go right to the A value. This thing is opening down. We can say the A value is negative. And if the A value is negative, this thing's opening down. That creates a maximum value. And what is the maximum value? Zero. Now, some people might say it's like some people might go ahead and say a max value of 0 at x equals 4. Because that's where the maximum value exists. It's 0 at x equals 4. And same with over here. Say something like, oh, the minimum value is negative 18 at x equals 1. Questions? It feels a whole lot better when you see this thing, you try it, you know, you give it, you try to fill in the table the best you got, and then you go and check it on Desmos, and things just start to make so much sense. Okay. Now, when you're given just a parabola rather than two equations, it's kind of nice. It is kind of nice. Because it's like, well, okay, well, for the given parabola, what are the zeros? It's like, okay, well, here's a 0, and there's a 0. Yeah? The zeros are x equals negative 1, and the other 0 is x equals positive 3, right? The equation of the axis of symmetry, well, we're going to draw that line of symmetry. Here's where I think it would be, you might agree, and that would exist at x equals 1, right? And it's like, well, think about it. We're going to take negative 1, oh, there you go, negative 1 and 3, add them together and divide it by 2, right? But you don't really have to do any of this because we have a graph and we can just see it. But just to show you the math works, that's where the math is coming from. We're taking the average of these two x-intercepts. And then the vertex, of course, it's right here where the parabola changes its direction. That looks like coordinate 1, 16. The vertex is 1, 16. Okay. The y-intercept is where the graph crosses the y-axis. Here we go, positive 12. Direction of opening, it looks like this thing is opening downward. A maximum or minimum, I think it's a maximum. Max is sad, right? Maximum. And then what is the maximum or minimum value, which is so nice to just look across here and say, okay, I think it's 16, yeah? Say max value of 16 at x equals 1. That's when it occurs, right? When x equals 1, the maximum value is 16. Okay. Folks, 3 questions here. Not a whole lot. But we do have a ton of time here. So how about we give that our best half an hour and see where we end up? Yeah? Make sure you use Desmos here because Desmos is the best way to confirm your answers. Yeah? So connect to the Wi-Fi, or if that's a struggle, stand out in the hallway for 2 minutes and download Desmos. It's free. It's a great app. I highly suggest it. Here, let me write that up there. So we've got page 155, 1, 2, and 7. And check your answers using Desmos.